This video will review the final exam materials for IS 555. About 60% of the exam will be on materials since the midterm. We've used a lot of the materials all the way through the class, including from the algorithms that we began with, like CART and MLR and so forth, and we've also used the materials on how to evaluate the quality of models and so forth from the beginning of class all the way to the end. So some of those materials will be in the midterm because we've been using them all the way through the course, and the remaining will be from what we've done since the midterm. Each student will be given 60 points for the exam as a baseline, and then you'll receive an additional point for every question that you answer correctly. And there will be around 45 questions in the exam, each worth a point apiece. So we talked about these topics since the midterm. We've talked about k-nearest neighbors, and then we talked about hyperlearners, the gradient boosting, the random forest, and support vector machines. So we're going to briefly review those and talk about some of the key aspects of those. We've talked about collinearity and singularity problems. These are problems when you have variables that are overlapping in their information and where the information in one independent variable is depending on the information in another independent variable. We need to manage these kinds of problems. So review those issues because there will be some questions on that from the exam. Also, we've talked about manipulating the probability cutoff or the thresholds, even though the standard 0.5 cutoff is what's used in data mining tools. There are times when it's more profitable or more effective to change that cutoff point. And we did examples of this where we were in Azure, we were sliding the cutoff around and how that changed the profitability, how it changed the number of true positives and so forth. So you want to look at that, and you're going to want to understand the basics of rock charts. We also did some clustering or subpopulations, how that can change the outcome of what you're trying to do. So sometimes there are subpopulations that are more effectively modeled as a subpopulation instead of a one-size-fits-all model. And we did some examples of using numeric input variables to create clusters through our machine learning. Most of this class has been based on supervised learning, where we have the known value of the outcome variable, and then we're using patterns in the data to be able to determine what the value of the output variable will be. We did some unsupervised learning when we did clustering, so that we use clustering to identify subpopulations. In that case, there are no right answers in the terms of just the perfect amount of subclusters, and there's no theoretically or empirical way of being sure that you have exactly the right subclusters. So it has to be done by some trial and error. And it can also be informed by visualizing pieces of the data and trying to identify trends in the data. The other thing we did is we did some processes to be able to figure out which variables were contributing to coming up with good predictions versus bad predictions. This is a good summary chart that talks about the algorithms that we've worked with and we've been able to practice with throughout the semester. You'll notice along the left area over here that we have which outcome variable types are dealt with by these variables. All of the algorithms that we worked with in this course can do both numeric and categorical predictions in the outcome variables. There are two exceptions. Multiple linear regression can only do numeric prediction. Logistic regression can only do categorical prediction. We also have some variables that require the use of dummy variables. In other words, the only way to get categories into the algorithms is to use dummy variables. MLR, logistic regression, and AN use dummy variables, and so does support vector machines. So if you're going to have categorical values in your input columns that need to be put into these algorithms, then it's going to be done through the use of dummy variables. Some data mining tools do this automatically, and sometimes, like the examples we worked on in Python, we actually had to create the dummy variables and eliminate one of the categories. Now KNN and boosting and so forth, they can use categorical values directly, and they do not need to use dummy variables when they are doing the machine learning. We also have some algorithms that have built right into them ways of determining which input variables are important. And then we have some that aren't. The first three that we dealt with throughout the semester was CART, MLR, and logreg. All three of those have the means built right into the algorithm itself to be able to determine which input variables are going to significantly contribute to the outcome variable. CART and CART does it by the tree. Those things that bubble up to the top of the tree are seen by CART as the most useful predictors. And then MLR and log-reg, they have which input variables are statistically significantly related to the outcome variable. In the method themselves, they're telling you what's important. And that's one of the reasons why we learned those early. Now, some have the ability to tell you after the fact which items were used the most. So for example, in AND, in some implementations of AND, after the network is built, then they will show you visualizations that show you, based on the network that has been built, how each input will relate to the output. Gradient boosting in the JMP implementation shows you how many times each of the input variables were used as splits to be able to make the trees. And so there is some post-processing built into some implementations of the algorithms that will tell you which ones of the input variables help the most. Random forests, support vector machines, and KNN, they don't really do that. You have to delete variables and see how deleting variables relates to your inputs, and you don't get as much direct signaling as some of these other algorithms in terms of what's important. In terms of interpretable models, CART, MLR, and logistic regression give you interpretable models that you can fairly easily understand how the inputs are related to the outputs. You know, they do that through trees or coefficients, and so that's a big benefit in terms of making explainable models. The remaining are really black boxes in the sense that it's very difficult to see how the outcomes are related to the income. One that's sort of in the middle is AND. You can actually see the trees, or you can see the graphs in AND that connect the nodes, and you can calculate the values of the nodes and see the weights on the trees. The problem is there's many calculations that are required to develop an AND, and so sometimes it's not worth showing that much complexity to the user. Should you standardize the data? The answer is sometimes it's not required. With CART and MLR, it's not required, for example, but there are a couple of algorithms where it's very important to standardize the data. KNN is very important to standardize the data, and a lot of the data mining tools will just do it automatically. And the same thing with neural networks, because if you have some variables that have high value magnitudes and some that are small, so if you have something like income that's in many thousands, and you have something like age, which is from 5 to 50 or 75, then the large values can swamp the small values in the calculations. And I show examples in the KNN deck of how that is accomplished. And so it is important or essential to standardize these. And the most typical way that is done is subtract the mean from each instance and then divide by the standard deviation to create a standardized value, and then use those as your inputs to be able to do the calculations. 3 of the 4 hyperlearners have a lot of overfitting potential. AND does, gradient boosting does, or we sometimes call it boosted trees, and then support vector machines. They tend to want to overfit, but they also can see patterns that some of the other algorithms cannot see. Random forests don't tend to overfit, because by building a forest of trees and then averaging across the trees, it sort of has a built-in control for overfitting. And so we have 3 that tend to overfit, and we just sort of have to watch those. Sometimes they can solve problems better than the other algorithms, but they also have a tendency to overfit, and you can tell how much overfitting occurs by looking at the difference between the model quality evaluations on the training and the validation, and the validation and the test data, and that'll give you an idea of how much overfitting there is. There's typically always overfitting when you go from one step to the next, and sometimes it's just a little bit and sometimes it's a lot. And if you see overfitting, that you're getting like 20% worse values in your validation data, you can tell that a lot of overfitting is happening. The models are too complex and they're kind of not working very well because they're overly complex. The next dimension of these models is in terms of the speed of training them and the speed of applying them. And in CART, CART and SVM are medium models to build. They take some time to go through, and in the case of CART, to find the best splitters, and an SVM to do the various tests to try to figure out what the best pattern recognition is. And so these are medium to build, but fast to implement. So CART has such simple models at the end that basically it's very fast to apply them. MLR and logistic regression are both very fast to build and fast to apply, and so their speed is one of the big benefits of those algorithms. KNN, slowness is its Achilles heel. Basically, it's slow to develop a model and slow to apply model because there is no model. The model is essentially using the instances of the other data points. So you pick the one that you're trying to predict for, and then you find the neighbors that are closest or the most like that one. Then you go to the next one that you're trying to develop an estimate for, and you find the nearest neighbors for that one. It's very slow to do, and it's very slow to apply. So generally for KNN, we only tend to do that when we have smaller data sets and we don't have a very large volume of columns, because those things will slow us down. If we have lots of records and we have lots of columns, KNN, its Achilles heel is its slowness. And can be slow to build, and one of the reasons why it's slow to build is because sometimes you may have to do 20 or 50 different starts because there's a random start involved in each and you have to do a number of starts to be able to allow it a chance to find good starting spots, which can be evolved into good solutions. So they're slow to build and fast to apply. Gradient boosting is amazingly fast to build and really fast to apply. So it like MLR and logistic regression is very fast, and so it's a really nice thing to do because it's really fast. Random forests are slow because instead of building one cart model, you might build 100 or 150 or 50, and it takes time to go through and do random forest because you're building so many trees and each tree is different than the other trees, and so that's slow. So KNN and random forest are really slow. Lastly, should you use a data set that is the test set? In other words, is a validation set good enough, or do you really need to do a test set? Like on Kaggle and other data mining competitions, will always use three test sets because they know that some of the people that are working in the competition are likely to use some of these algorithms that use 3 sets. That is a training, validation, and a test set. Why you need a test set is because sometimes with some algorithms, overfitting is introduced in the validation data. So how is that done? In the cart model, overfitting is introduced when the tree is pruned. So you train on the training data, and then we prune the tree using the validation data, and because a specific partition of the data is used for the training, that may impact how the model is going to be pruned. And so you can introduce overfitting in the validation phase. KNN introduces overfitting by picking which K is the correct K. So when you use the validation data, you have to go through and determine which K is the best K. So you can introduce overfitting by having the validation data used for that purpose. So another way to think about this is if the validation data is different from the test data set, then you can tune to the validation data, but then when you apply the test data to it, if it's not very similar to the validation data, then the test set can be worse and sometimes better than what you get out of the validation data. And does overfitting with the validation data because the validation data is used to tune some of the model parameters. So overfitting is introduced in validation there. And SVM does too. So SVM's parameters are tuned with the validation. So for 4 of these algorithms, you really need to use a test data set. So if you're in a data mining competition and you were not sure which of the algorithms were going to be best, and it might be that these 4 that sometimes introduce overfitting in the validation data, you should use test data on your algorithms because those would be allowing you to compare apples to apples across all the algorithms.